we can write them alloy systems. So some places we can use word systems or alloy systems. So that system is coming from here on the alloy systems. Now, so phase diagram are the maps that gives the relationship between phases in equilibrium in a system as a function of temperature, pressure, and composition. So these three things are very important. So these are relationship between which is a function of temperature, pressure, and composition. T, P, and C. So the knowledge and understanding of phase diagram is very important for the engineer to relate to the design and the control heat treating procedures. If you want to design, you want a soft you want stainless steel or you want a steel. Both are different things. Okay, you want a hard material which are high temperature magnetic properties, like you want titanium alloys, you want normal titanium. You want superalloys which you use for turbine engines, jet engines, or your normal alloys which can use below 100 degrees Celsius to 1000 degrees Celsius. So all these information, what between the phases information, at what temperature we should do the heat treatment, how we can control the microstructure properties, and microstructure properties affect the mechanical properties. So all their thermal histories, all this information we are getting from the phase diagrams. Okay. The question comes, how you define a phase? So I give an example of H2O molecule. H2O molecule, one is ice, one is water, one is gas. The same molecule is present in three forms. So I can say within, so all they are chemically homogeneous. So phase is a chemical homogeneous identity. One, you can separate them. They are distinct. Ice is distinct from water. Water is distinct from vapor. So they are physically distinct. Mechanical separable. You can take it out ice from water, and vapors will evaporate from the water. So they are mechanically separable also. So phase is a physical, distinct, chemically homogeneous, and mechanical separable identity or region of a system. Okay, that is the definition of phase. So for example, gas. So gas states always a single phase. So you mix any gas, like air also has many. You have nitrogen, oxygen, carbon. So it's a mixture of gas. So it's always in a single phase region. So it is independent of what kind of gas you are using, what is structure, whether it's atomic gas or you are using molecular gas. So they are mixed at atomic and molecular level. When I'm coming to next, liquid. Liquid also are single phase. Okay, kind of single phase. They are not mixing in gases. They are mixing, but they are not mixing at atomic and molecular level. Okay, like you cannot you can mix sugar in a water some extent only. After that, it will precipitate out. Same thing happen with NaCl also. And oil will not mix with water; it will float over it. So atomic and molecular level there is no mix. So no mixing at okay. That is how liquid is different from gases. Third one is solid. And solid, in general, due to several composition and crystal structure, there is a possibility you have many phases are possible in solid. So, like I am saying, giving example of iron. Iron is an element. Okay, this element at room temperature it is BCC. If you go little high temperature, like above 910 degrees Celsius, it's become FCP. If high pressure more than 15 gigapascal, it is SCP, and 1400 above, it is BCC again. Okay, so within same element, it present in different phases. Okay, so structure is different, phase will be different. Always remember, like for same composition, same iron, which is 100% iron, it having the different structures. It means different structure repeat different phases. So iron BCC is different phase, iron FCC is different because the atomic arrangement between them is different. Okay, that's the reason. Now, how we know how many, if you mix that many elements, like I mix copper and nickel or aluminum or copper, how many, I suppose I mix aluminum, in that I have added 50% copper. Now I add it and I heat it and melt it and start cooling down it. Now when cooling down, whether I'll get pure copper or pure aluminum? No, not necessarily. You may have an intermetallic also possible. You may have Al2Cu phase, or you may have aluminum solid solution, copper solid solutions. Okay, so there is a different phases are possible during solidification. But how we decide how many phase will form? So system will decide what that phase will form. So for that Gibbs given a rule. So that rule is called P plus F is equal to C plus N, where P represent your number of phases present in that system. F represents the degree of freedom. Okay, how many ways freedom means how many ways, whether any variables are here, your temperature, pressure, and composition. So all these are independently you can vary, or they are dependent, or two component dependent, one is independent, or one component, or two, one is independent, two is independent, one is dependent. And represent here capital N, you are saying here, that represents two variables, external variables. One is temperature, one is pressure. Okay, so N is nothing, basically it represents temperature and pressure. So this equation will become if I put, so there are two external variables, this equation I can write in this form also. P plus F is equal to C plus 2, or I can write F is equal to C minus P plus 2. So this final equation generally we used. So this equation also get modified for binary phase diagram or some other phase diagram, equilibrium phase diagram. So it says that if we are drawing phase diagrams, okay, we are consider okay, if your pressure is 1 atmosphere throughout, so this equation will get modified, that will become F is equal to C minus P plus 1. So both equations are basically we use in this equation and this equation also. But if it is given that at a constant pressure, then we have to use F is equal to C minus P plus 1. If your pressure also variable, temperature also variable, then we use F is equal to C minus P plus 2. Now, like one more, N is 2 for, generally it's always remember. And we for unary phase diagram, where is a single component. When I'm saying binary phase diagram, single component, your composition is constant here. Okay, composition. Okay, or composition, or you can say component here. Components. C. This is only one constant. That is fixed. But P and P are variables. So this equation we are using for unary phase diagram. This for unary phase diagram. This. For this one, binary phase diagram, this equation becomes F is equal to C minus P plus. This for binary. So this is Gibbs phase rule. Let's take one where normal equation only, C F is equal to minus C minus, so C minus P plus 1. So what your degree of freedom depends upon what? Two things is different. Basically, it's a difference between the component which you can control and which system will control. So how many elements have to add? 1, 2, 3, 4, 5, 6. That is in my hand. So the metallurgist, the person who is developing that alloy, that control can control C component. But how many phase will evolve? That will decide by P will decide by the system itself. Okay, system is the elements which are mixing, that will decide after mixing what will happen. That is not in our hand. So I can say F is equal to C plus 2 minus P. So C plus 2 is the temperature and pressure that also we can control. So degree of freedom means how many of variables we can choose independently, and that depends upon what we can control. So we can control components, number of components we are adding, and the temperature and pressure in that condition which we are allowing and making that alloy. And the P is the system will control. So system will decide how many phase to produce at the given condition. So this is basically the idea behind this one. Okay. Now this is just small exercise we are doing here. So what is the degree of freedom of a system of two component? Two component is coming means C is equal to 2. When the number of phases is 1, 2, 3, 4, 5, 6 and so on. So number of phases I put in this table. Total variables are P into C minus 1 plus 2 and degree of freedom. Okay, F is equal to C minus P plus 2. Now if there is after solidification, ultimately you end up with only single phase. The phase is 1. So if you put P is 1, C is 2. So 1 plus 2, that will give me 3. So there are total 3 variables. Okay. So 3 variables and degree of freedom will be much component 2. P is 1 plus 2. Okay, again 3. So degree of freedom also 3. So in a single phase region, where there is a liquid, let's say liquid, you change pressure, again it will remain liquid. You change temperature, again it liquid. You change component with composition here, I would say. So that also again you will have liquid only. So I can say all 3 variables, C, pressure, temperature and composition. All 3 variables you can have independently, you can vary when phase is 1. Okay. When you increase phase 1 to 2 phases, binary phase. Okay, 2 phases are involving. So if the number of variables will be 2 into 1 plus 2. 2 plus 2, 4. So total variables are 4. But degree of freedom kitna? 2 minus 2, 0. So give me 2. So degree of freedom is 2. It means one of the variables is fixed. So if you generally in that case we take temperature, pressure is fixed. So your pressure is fixed. So you can vary temperature and composition independently. So at different composition you have a different temperature. At different temperature you have a different composition. Okay. Now degree of freedom is 3. So the number of phases is 3. So your variables will 5, but degree of freedom is 1. So it means only one component is very independently, others are dependent. Okay. When it is 4, there is no degree of freedom. All the variables are 6. Degree of freedom is 0. It means that is a invariant point. That if you change from move that point, your variable will change. Means your temperature, pressure, composition will change. So at a fixed temperature and pressure, you have that composition. So there is no degree of freedom. So I can say the system cannot now. If you go number of phases 5, degree of freedom is not possible. Minus F cannot be minus 1. Okay. So maximum phases possible is 4. Okay. According to Gibbs phase rule, maximum phases possible how many? 4. For that degree of freedom is 0. In case of unary phase diagram, I can say. Okay. But at 1 atmosphere, pressure is fixed. So Gibbs phase rule change F is equal to C minus plus 1. In this case, the system cannot have more than 3 phases in maximum. In that case, your number of phases is 3, or P is 3, and C is 1, and in place of 2, we have a 1. So it becomes, here is 3 plus 1, 4. Okay. and degree of freedom is C is 2, phases is 3 plus 2. So degree of freedom will be 0. For number of phases of 3, that means in case of binary phase diagram, most of the times we will maximum phases you can which exist equilibrium coexist, that is only 3 phases. You cannot have more than 3 phases. So this is reasoning question they have asked many times. Why in binary phase diagram at 1 atmosphere pressure you can maximum phase exists is 3? Explain. So some more terminologies. One is like I'm using equilibrium phase diagram. So equilibrium state is always minimum energy state for a given temperature and pressure composition kind of in a phase diagram. Okay, and this implies this state will persist indefinitely. It will remain there, means this state. It will not change. So equilibrium phase diagram will stay constant over time. So phase diagram tell us about the equilibrium phases at a function of temperature, pressure, and composition. That I have already mentioned. So we keep in binary case pressure constant, and for normal unary case pressure is not constant. Now some more terminology like phase equilibrium. One is thing is solution. So solution is nothing, is a basically single phase. So solutions can be in gaseous phase, they are single. Liquid when they present solution form, they are also single phase, or solid also single phase. In that, like liquid, you can mix NaCl and water liquid, so that is a solution. Okay, so whereas in solid also you can have solid solutions, like in I given example earlier also, copper nickel is solid solution, silver gold is solid solution, germanium silicon is solid solution. So we have to go home rule 3 rule. When I'm saying mixture, so mixture is more than one phases. More than one phases. It's a mixture. Like you mix different kind of dals, so you ultimately can identify which dal is what. So that is a mixture. That is not the solution. Okay. Okay. Now solubility limit, like I am adding in sugar in water, it will keep on dissolving. But at room temperature, ultimately it start precipitating out. It's not more dissolving. The solution it will dissolve. We call it a syrup, and then it precipitate out. Then we have a syrup plus solid sugar. Like this is the phase diagram of you are saying of water and sugar phase diagram. So in this phase diagram, one end you have a water, other end you have a sugar. So water, if you are 0%, 0, so this composition is along axis, that is represent the C represent the composition weight percent, and y axis is temperature degree Celsius. So it's saying the maximum solubility of your sugar in water, it can dissolve, it remains form a solution. It is 65.8% sugar if you add in water at 20 degrees Celsius, less than 20 degrees Celsius, it remains in in solution form. At 20 degrees Celsius, if it is less than 20, 65.8%, it is a solution form. If you go beyond 65.8%, you will end up with a liquid plus solid. Okay, or you can say 25 degree above 65 degree, and this solubility limit is increasing. Okay, so like at 80 degrees Celsius, 80 degrees Celsius में limit कितनी है? 80 से आप एक line draw करो, that will cut by this curve. Okay, so this curve is cutting, so my solubility is how much? Roughly 75 to 78% here. So basically my solubility limit has even increased at 75 weight percent sugar at 80 degree Celsius. Okay, 100 पे तो और बढ़ जाएगा. 100 डिग्री पे कितना होगा मेरा? 100 डिग्री पे solubility roughly 80%. 80% हो जाएगा. 80% sugar will dissolve. So that's why reason आप देखोगे in household also you take a water, add sugar, and after some it will precipitate. Now heat it, so sugar will start dissolving, because what happens, water molecule will start widen and sugar molecules will start going inside. So your solubility limit will increase with increasing temperature. So this is the simplest diagram, sugar and water simple phase diagram. So this is binary phase diagram. Now coming to the unary first phase diagram. So unary phase diagram like iron, pure metallic phase diagram basically. So there is no composition variable. So composition variable doesn't meaning is less. It's meaningless basically because I know the full material is made of one kind of element. So composition is meaningless in unary phase diagram. So C is one here. So other two component is which are variables temperature and pressure. So the phase diagram, unary phase diagram, always we plot in pressure, temperature versus pressure. Temperature versus pressure. So this is one of the phase diagram, unary phase diagram I am discussing here. This one is basically iron phase diagram. Okay, iron phase diagram, pure iron phase diagram. Okay, at room temperature, if you see from room temperature to 910 degrees Celsius. Okay, and your alpha is phase is present. This is the boundary, and above 12 gigapascal, if you apply the pressure is continue, your material will change into epsilon phase. If I am going above 1000 degrees Celsius, pressure is low and pressure is increased by axis, so it will change into gamma. It's like that I can say at 10 gigapascal, it will change into gamma phase at lower temperature itself. Okay, 500 पे ही gamma बन जाएगा at high pressure. Okay, if the pressure is 5 gigapascal, gamma will form from alpha at 700 degrees Celsius. Zero, if there is no pressure at all at 910, it will change into gamma alpha. और ऐसे below में भी ले सकते हो. If pressure पे, this will change into gamma. So all phases in phase diagrams we represent by Greek letters. Like alpha means alpha is basically iron. Okay, this is iron only for BCC. Okay, gamma is stable at high temperature. This one is more than 900 in this range, 900 to 910 to and 1400. You can say right. This one is FCC iron. Okay. Now from delta gamma, it will change into delta only for few range only. So this is my pressure range only. So roughly 3, 4, 5, and this one is 2 gigapascal, and temperature is below 1500. In that range only, your delta is stable. The delta is what? Delta is a structure which is basically again Fe BCC. But if I increase my pressure increase करता हूँ, यहाँ लेवल तो एकदम ही गामा बन जाएगा, डेल्टा नहीं रहेगा. So these boundaries you can see above this one. So these boundary defining something. So these boundaries are very crucial. Okay, like one boundary is here. This one. This is a boundary which is separating alpha and gamma. Okay, and one boundary we have between which separating out alpha and epsilon. Okay. One boundary is this which separating out gamma and epsilon. Okay. And this one boundary is like this. Okay, this one is one boundary which separating gamma and delta. This is delta and liquid. Okay. Let me put different. The different boundaries are there, and this one is separating liquid iron and gamma, and this one is then we have vapors. Okay. You have vapors, gas. So alpha is stable in this region, epsilon is stable in this, gamma is stable in this region, liquid and gas is with temperature. So I can say, you can see your if you're increasing, temperature is increasing, pressure is increasing. So gamma, as pressure increasing, there is a temperature increment only. Okay, when we change gamma to liquid, same gamma to, so liquid to gas. This is increasing with increasing pressure. So pressure के साथ क्या हो रहा है तुम्हारा temperature, you can see with pressure melting point also increasing. आप देख लो खुद भी pressure की वजह से melting point मेरा बढ़ रहा है. So initially melting point of iron is, this is pure iron, this is 1535. 5 मेगा गीगापास्कल pressure, वो pressure temperature कितना हो गया? That is close to 2000 degrees Celsius. 10 पे कितना हो गया? Your melting point, that is more than 2000 degrees Celsius. So they are interrelated. If you change one, another will also change. So it's like, now here let's see something. When C is 1, phase is 1, like we see alpha is there or gamma is there, liquid there, gas is there. So degree of freedom is F is equal to 2. So both, so in this region I can, in this region like single phase, this also a single phase, this also a single phase, this also single phase, this also single phase. In all these regions I can vary temperature and pressure independently. Okay, boundary पे नहीं कर रहा हूँ मैं, but within this region if I change pressure to this one or temperature, both remain like alpha only. So within these regions you can independently vary temperature or pressure, doesn't matter. Your phase will remain single only, alpha. Now, so degree of freedom is 2. So you can vary independently temperature or pressure. That's why degree of freedom is 2. When C is 1, phases are 2. Phase 2, two phases where they are present at grain boundary. Okay. So they are the grain boundaries here. So this is one grain boundary. Okay. So at grain boundary, how many phases present? Alpha and B gamma. 2 phases are present. So degree of freedom will reduce. Degree of freedom will change. Why? Either temperature or pressure can be varied independently, but not both. दोनों को साथ नहीं वेरी कर सकते. क्यों? देख लो, अगर मैं प्रेशर चेंज करता हूँ from here, okay, this is my where this is a transition temperature where alpha will change into gamma. Whereas I change pressure 10 gigapascal, this transition had reduced. So it means you cannot handle them independently. So एक को change करोगे. So either temperature or pressure can be varied. Whereas in first case, when phase is 1, you can vary independently within that. Now we see third one. So two phase boundary region. These boundaries are basically where both phases are exist. Now 3 C is equal to 1, P is 3, F is equal to 1. When that is the case, your degree of freedom is 0. Okay. FC minus P, 1 minus plus 2. Okay. So degree of freedom is basically 0. अब degree of freedom कहाँ 0 होगा? That is where 3 phases are boundaries are in matching, in joining. So this triple point, this is one point, this is another point. So here at this condition, your temperature, pressure, both are fixed. So this point will exist at a particular temperature and particular pressure. Okay, you cannot handle them independently at all. So 3 phases will coexist at one particular point, combination of pressure and temperature. So this is one unary phase diagram I have discussed how to read out this one. Okay. Now I am coming to, so I can there are 3 topics I'll discuss. So this is my first topic. So where I discuss the phase diagrams is the basically relationship of different phases of material in equilibrium with variables. Second is solid can have more than one phases based on their crystal structure. Third, in liquid and gases, the phases can be identified based on miscibility Okay, whether they miscible or not. Gas always has single phase.